Okay, hello everybody and welcome to the first session of our webinar in this year 2023. Yes, and we are very happy to have you all again with us in this opportunity. Today our speaker will be Professor Carlos Olmos from Universidad Nacional de Córdoba, and he will talk today about totally geodesic submanifolds of Hopf-Berger spheres. Well, thank you very much, Carlos, for accepting this invitation, and it's all yours now.
Well, no, thank you for all the organizers, to Adrián, Juliet, Paolo, Enriquez, and Luis for the kind invitation. It is a pleasure and an honor to me this invitation. So I will begin with totally geodesic submanifolds of Hopf-Berger spheres. So the problem of studying totally geodesic submanifolds is a very difficult problem in general to classify totally geodesic submanifold, even in symmetric space. Though of course in symmetric space totally geodesic submanifolds are related to the well-known Lie triple systems, but the classification is only known for rank 1 and rank 2 after several papers, Chen, Nagano, and then also recently Andreas Kollross and Alberto did the classification for exceptional symmetric spaces. So here, let us begin. So this is the general contents. So in the 30s, Hopf introduced the so-called Hopf vibration. So the Hopf vibration, the first one is the complex one, the second is the quaternionic one, and the third one is the octonionic. So when it is said OP1, this is the octonionic, this is nothing else than the sphere of dimension 8. The sphere of dimension 8. The line, the projective line over the octonions is a sphere, but not the plane. Okay. These vibrations play a fundamental role both in geometry and topology. Excuse me, since I cannot see anything else, so it is okay, the sound and...
It is okay, yes.
Yes, it's okay, okay. Thank you.
Because sometimes happen to me that nobody speaks, but the connection went out. I hope that this will not happen. This vibration play a fundamental role both in geometry and topology, the Hopf vibrations. So the base space has the Riemannian symmetric metric of maximal sectional curvature equal to 4. We put that this is more so for doing calculations we can assume that a maximal sectional curvature 4. So the base space could be a sphere. In that case, the sectional curvature is exactly 4. But in general, it's a symmetric rank 1 space, and the curvatures are between 1 and 4. Hopf vibrations are Riemannian submersion with totally geodesic fibers. So Hopf vibration, so you can see, for example, the usual the so-called Berger sphere in dimension 3. You have in the 3 sphere you have you can regard that as a sphere in C2, and then the action by multiplication of scalars of unit length, and then this gives the so-called Hopf vibration in the complex case, and this is very well known. So Riemannians, so this is general facts, very difficult deep facts. So from Gromol, Grove, and finally Wilking, Riemannian submersion from a round sphere with connected fibers of positive dimension is metrically congruent to the Hopf vibration. So, and now, so you have a sphere and you have a fiber. So we rescale the metric, but only we rescale only in the vertical directions by a factor tau. Only on that. Otherwise, we get the homothetic space. So if tau is 1, we have a round sphere. So a round sphere of dimension 2n plus 1 or dimension 4n plus 1 in the quaternionic case, excuse me, 4n plus plus 3, or is in the Cayley case, the total space is a sphere, X15. So we will assume that tau is different from 1, otherwise we get the round sphere. These are called the Hopf-Berger spheres. Berger spheres is when in the complex, and so I don't know if it is probably not a very standard notation, but it's clear that the Hopf-Berger sphere, what does it mean? Somebody, I think, told me that sometimes Berger spheres are called when tau is less than 1, and when tau is greater than 1, they are called anti-Berger sphere or something like that. But if you look in the literature, but we call all the Hopf-Berger spheres. And we will call Berger sphere when in the special case of the complex numbers. So a sphere of dimension 2n plus 1 in Cn. Okay, the notation, this is only notation. So what I said, these are the dimensions. So one is using the complex vibration, the quaternionic, and the Cayley vibration. So the great difference between the first two and the last one is that in the first two there is a group action that gives the fibers S1, or in the other case SP1. But in the quaternionic case, of course, the fibers are 7-dimensional. Pardon, excuse me. In the octonionic case, the fibers are 7-dimensional, totally geodesic, also spheres. But it's a homogeneous. Every fiber is homogeneous, but there is no group giving all the fibers. This is the main difference. So when not specified the type, a Hopf-Berger sphere is denoted by in this way. When we will not specify the type of the Hopf-Berger, the vibration. So this is appears in a paper by Bardiani-Siller. I think it's not, we will not find it in any other place. I think it's a Hopf-Berger sphere has positive curvature if and only if tau is less than 4/3. So not all Hopf-Berger spheres. So this type of spaces are very well studied because of mostly in the case of positive curvature. So, and also Hopf-Berger sphere, and there is another are the homogeneous spaces that are homeomorphic to spheres, and then there are some more spaces, some more metrics in general, but this is it's also a special case of homogeneous, but a very important case of homogeneous spaces diffeomorphic to spheres of positive curvature. When tau is yes.
Carlos,
See.
One question: in what year was this proved, approximately?
No, in a paper of Verdiani-Siller, they say that, but usually we don't know if they have, digamos, they calculate explicitly that, but probably that could be known before.
Okay.
I put this, but I don't know. Probably this, probably this was known by Siller much before.
Okay, thank you.
Yeah, so I put there no reference, but so you can find in a paper of Verdiani-Siller. Any Hopf-Berger sphere, which is not a round sphere, may be regarded. This is very important. This observation. So made by Siller in some paper many years ago in the 70s. I don't know. So what happened with this thing is that they say this happens, but they don't claim that it was the first time, or probably even it could be known before, but we found in a paper of Siller. Maybe regarded as geodesic spheres of rank 1 symmetric spaces. So geometrically, we will use this fact for doing geometry with the Hopf-Berger spheres, because they can be regarded as geodesic sphere of a rank 1 symmetric space. Not so a rank 1 different from not a space of constant curvature, because the geodesic sphere of a space of constant curvature has constant curvature. Of course, we are not studying this case. Okay, and so there are around one symmetric space. So, and conversely, of course, this is clear. Any Hopf-Berger sphere is any geodesic sphere is a Hopf-Berger sphere. Okay. So if we choose, if we fix the symmetric space without rescaling with the curvature between 1 and 4, then of course is homothetic to that. We need a homothetic, and now we will write explicitly some formulas. So of course the curvature between 1 and 4 in the compact case, and between -4 and -1 in the non-compact case. So the isometry group of a Hopf-Berger sphere, the full isometry group, can be regarded as since they are a geodesic sphere, so with center O, and then the isotropy of the ambient space acts transitively, but moreover, this is the full isometry group of a Hopf-Berger sphere. So, and here are the explicit calculation. I think there is a book of Bettiol and something else. I think there are explicit calculation of this. One can do using Jacobi fields. And then, so the precise relation is this. So in general, in the non-compact case, the non-compact case corresponds with tau. So the geodesic sphere, a Hopf-Berger sphere can be realized as a geodesic sphere if tau is greater than 1. You need the ambient space to be non-compact, and in the other case, compact. But nevertheless, so all geodesic spheres of when the ambient space is compact have positive curvature, and for the non-compact, they have positive curvatures up to the parameter equals to some radio. You can calculate explicitly up to some radio only. because you remember, so tau positive curvature is when tau is less than 4/3. And then, so positive curvature you find both in the compact and in the non-compact case for geodesic spheres, but not in some cases for the non-compact. So the fibers of the Hopf fibration from a Hopf-Berger sphere so if we will use the model of geodesic sphere, and so we want to see what are the fibers of the Hopf-Berger spheres in this model, and they are the intersection of a Helgason sphere that contain the center. Helgason sphere is a sphere that has the maximal curvature 4, a maximal dimension, and all of them are conjugated. So Helgason sphere, for example, in the complex Helgason sphere in CPN has dimension 2. A Helgason sphere has dimension 2. In the case of the quaternionic has dimension 4, and in case of the octonionic in the Cayley plane, it has dimension 8. But since we intersect with the geodesic sphere, we get the fibers of the dimension, for example, dimension 1. So dimension 2 intersected with geodesic sphere gives dimension 1. Dimension 4 intersected gives 3, and in the other dimension 8 gives dimension 7. So you can regard in this way the foliation, the Hopf foliation. Okay. So in the Cayley plane, so the totally geodesic submanifold of dimension 8, you have no totally geodesic submanifold of dimension greater than 8. So it has just the half of the dimension of the space. Has this Helgason sphere in the Cayley plane of dimension 16. So you get Helgason sphere of dimension 8. Well, Hopf-Berger spheres are geospaces. Geospaces means that the geodesics are given by the orbit of a one parameter group of isometries. Moreover, so the Hopf-Berger spheres are naturally reductive spaces. So they are very well studied. So naturally reductive spaces, there is a subspace of the algebra which gives all the geodesic some reductive recomposition. This is not true in the octonionic case. It's only a geospace, except for a special case of the parameter, which is tau equals 1/2, because the parameter you can use in any type of geodesic sphere. You have the type of the geodesic sphere, complex, quaternionic or octonionic, and then you have a tau also. But in the octonionic case, when tau is 1/2, in that case the space is normal homogeneous. That is more than natural reductive. In particular, is natural reductive. So we will focus our attention on the geometry of Hopf-Berger spheres, and very in particular on totally geodesic immersed submanifolds. Because when we study totally geodesic, so we cannot assume that the totally geodesic is embedded in general as a geodesic, for example. In general, you cannot assume when trying to classify. We will show a classification of such submanifolds. There are some of such manifolds are the standard ones. If you intersect a geodesic sphere with a totally geodesic submanifold, it is a very general fact of the ambient space that contains the center, of the geodesic sphere, then you get a totally geodesic submanifold. So these are the standard ones, and we at the first stage we suppose that there would be no more than these standard ones. As for example, in the sphere, we are not considering this case, but the sphere is geodesic sphere, and then any totally geodesic submanifold is obtained by intersection with totally geodesic with subspaces. So it's the same phenomenon. But surprisingly, for tau less than 1/2, except for the classical Berger sphere, in classical Berger spheres there are no all totally geodesic submanifolds are given by intersection, but one has to be careful. Totally geodesic submanifold of dimension at least 2, because any the geodesics for example, in the three sphere, the Berger sphere, so are not intersections of a plane of the space, for example. And then this is true because we are assuming that totally geodesic submanifolds are the dimension at least 2. So for tau less than 1/2, we found some exceptional totally geodesic round spheres. They are totally geodesic spheres of the same dimension of the fiber, but which are in a different position and which are not congruent by the isometry group to the fiber, of course, because the isometry group maps the fiber into the fiber. But this we can call exceptional, that you just intersect with some Hopf-Berger sphere, but that not contain, with Helgason sphere, but that not very particular, that does not contain the center. And this we can call here for the talk exceptional, because you can develop some theory of that, and you can construct geometrically this. But surprisingly, there are other totally geodesic submanifolds that are isomorphic to RP2 and to RP3. For example, this RP3 only for the quaternionic case and only in dimension 11 or more. And this is the... So we will... in particular, we found the totally geodesic RP2 in a 7, in the 7th sphere of dimension of the Hopf-Berger with tau 1/3, because if we put other taus, we have to increase the dimension. In this case, you can go no further than 7 dimensions to find the RP2. So what is somewhat, of course, in the sphere there are the Veronese embedding, but not totally geodesic, one knows. But in general, there is an obstruction of Wilking. This is the so-called connectedness principle of Wilking, that if the codimension is small of a totally geodesic in positive curvature, recall that we are now in positive curvature because tau is less than 1/2 or 1/3. So in positive curvature, there is some obstruction of Wilking, the connectedness principle, that say that the totally geodesic manifold of small codimension must must be connected. So the immersion has to be an isomorphism in the fundamental groups. In the fundamental groups, from the homotopy groups, up to some, but in particular, from Wilking theory, for example, an RP4 totally geodesic cannot exist in positive curvature so if you have an X7 of positive curvature, then you cannot have an RP4 totally geodesic. But now, so we construct that RP2 you can find, and we do not know, and probably not, that if they would exist in a space of positive curvature, in a sphere of dimension 7 with a metric of positive curvature and RP3. So this is only to illustrate a little, so this construction or this result. Okay, so we will begin with well-positioned totally geodesic submanifolds. What does it mean? So you have what does so let us begin. Let us follow the file. The intersection, what I said of geodesic sphere, this is a general fact. I recall what I said before. With a totally geodesic submanifold that contains the center is totally geodesic. In general, we need that the sigma is contained in the domain or normal coordinate, but otherwise it could come back. But in a symmetric of rank 1, we manage, so it's exactly that. So we don't know to do further assumptions. So a totally geodesic submanifold of a Hopf-Berger sphere is well positioned if the totally geodesic submanifold at any point, so the tangent splits as the direct sum of a horizontal subspace and a vertical subspace tangent to the fiber of the vertical. So this is well positioned. In general, well positioned, I think there is a result of Eschenburg, some paper, that in general, if you have a Riemannian submersion and then you have a well-positioned totally geodesic submanifold, and you in the fiber we do the same as we do now, that you perturb by a factor tau in the fibers, then the manifold itself, you do calculations, and the manifold itself is totally geodesic for any tau. So because of that, we are speaking about well-positioned submanifolds. So if for all t, you have this splitting. So if you intersect with the totally geodesic of the ambient space, we get a well-positioned. And conversely, if you have a well-positioned, then you have a totally geodesic you pass to parallel spheres, and then you construct a totally geodesic of the ambient space. So these are the good. So it's equivalent to have a well-positioned totally geodesic to have that the totally geodesic manifold in our case is the intersection of a totally geodesic submanifold of the ambient space. So this is the good thing.
So Carlos, you mean the horizontal space with respect to the metric for tau lesser than 1?
The horizontal space does not change. So because I am so this so the vertical space and the horizontal space. So if you like, you can put the round metric, but so this does not depend on this part of the talk. That does not depend on the tau.
I see, but you are assuming that each of the summons are not trivial. I mean, like for each.
No. It could be vertical or could be completely horizontal. So we are not assuming that.
I see. Thank you.
Maybe you could explain what is forbidden, right? What would be not well positioned? Maybe you can explain what this is trying to forbid. So how could you not be well positioned?
If you, I don't hear properly, but I think I guess what you think is why if you intersect with the total geodesic of the ambient space, why it's well positioned. You mean that?
Yeah. What's the opposite of well positioned?
Yeah, it's well positioned. I will give I will explain then in the paper in the talk. But the main fact is that the tangent is invariant under the shape operator, and the shape operator of the geodesic sphere has only two eigenvalues. O sea, the shape operator leaves invariant the horizontal subspace and the vertical, and has different eigenvalues. And so being invariant under the shape operators implies that, and this is standard to show that if you get a totally geodesic intersect with a totally geodesic that contains the center, this is invariant under the shape operator of the sphere.
Okay.
This is the main fact. I think we will, in next slides, we will comment about this. Okay. Now let V. So this is very crucial because for the first thing we knew for attacking the problem, but otherwise, let V be either a horizontal or a vertical vector for any chow, a horizontal or vertical. So, and then this is a calculation. It's not difficult, somewhat standard, that the Jacobi operator R is the curvature tensor of the geodesic sphere. For calculating this, you have to use the shape operator and the well-known Gauss formula, and then you calculate the curvature tensor of the geodesic sphere. And if you get this Jacobi operator, leaves invariant the horizontal and the vertical subspaces. This is a calculation. O sea, I said before that the shape operator leaves invariant, and they have exactly two eigenvalues, one different, one for the horizontal and one for the vertical. Here is the same, but there could be many eigenvalues or more than one. But the key fact is that the eigenvalues respect to the vertical direction, because the vertical space is invariant, and the horizontal, the eigenvalues are completely different. O sea, are different. There cannot be that an eigenvalue of the Jacobi operator restricted to the vertical space is the same as an eigenvalue of the Jacobi operator of this, no? V vertical or horizontal, so different calculations, and restricted to the horizontal have different eigenvalues. So now this is what things, and now if you have a totally geodesic submanifold, then the totally geodesic submanifold you choose. Suppose that the totally geodesic submanifold of the Berger of the geodesic sphere has a vertical, or either a vertical or a horizontal, or both vectors, then the tangent space is invariant under the Jacobi. But this is a problem of elementary algebra, that if something is invariant by some transformations, symmetric transformation, and then it splits as the direct sum of subspaces of the eigenspaces. But the eigenspaces are different. The vertical one that the horizontal one. Immediately from this observation, we get that the totally geodesic submanifold that has either a horizontal or a vertical vector splits. The tangent splits as the direct sum of a horizontal and vertical. So it's well positioned. So this is very important, because if the dimension is greater, so now we will see in the formula. So here is in the file what I said. So any horizontal eigenvalues is different from any vertical one, and what I said before, this implies that the totally geodesic submanifold that contains the horizontal or vertical vector is well positioned. So suppose that your totally geodesic has big dimension. In the case of the complex, big dimension is dimension. So if the totally geodesic has dimension at least the dimension of the fiber plus one, dimension of the fiber plus 1, or dimension of which is the same of the field. For example, in the complex, you need that the total geodesic has dimension greater or equal than 2. So these are the usual that we are treating. And so this immediately implies that the total geodesic is a manifold of a Berger sphere. So not a Hopf-Berger, so a Berger sphere in the complex case, since the dimension is 2 and the fiber has dimension 1, has to intersect the horizontal subspace, which is a hyperplane, the horizontal subspace of the tangent space, and then it has always any total geodesic of submanifold dimension at least 2, so not a geodesic, has a horizontal vector, and then by the other thing, what I said, is well positioned, and if it's well positioned, it is obtained by the intersection of total geodesic of the ambient space, and in this way we solve completely the problem there. Then this well positioned at the every point. So we have this theorem. So I should say something that there is a paper, I do not put here in the reference, I will, of Torralbo and Urbano. There is a paper, but they do analysis and they prove for tau less than 1 this result, but with a point of view not geometric, but more from the analysis, because they are doing minimal surfaces or something like that. O sea, for tau less than 1, o sea, for this was known by Torralbo and Urbano. So I will add well, I put no reference here, but now we have this theorem, the general theorem. So it is equivalent. So another thing which is very important, I think I probably here, proposition. If total geodesic is well positioned at some point, it will be well positioned at any point. This is so one can prove such a thing. Only with 1 point is enough for all points. Okay, and here is the general for well positioned general theorem. Sigma is well positioned, totally geodesic, submanifold of the Hopf-Berger sphere, is equivalent that has a vertical, a horizontal non-zero vector for every, and because of proposition before for some, you can change every for some. The tangent space is invariant under a shape operator is the same, because it must split, because it has two only eigenvalues, a vertical and a horizontal one. And well, this is what I said before. Here is announced as a theorem. Okay, we continue. Here is the list of well-positioned total geodesic manifolds. So are spheres. So a well-positioned is intersection of a total geodesic three-dimensional space. So it's a geodesic sphere intersected with a total geodesic submanifold that contains the center is also a geodesic spheres. So in particular, the well-positioned are geodesic spheres. So, but here, the geodesic spheres are Hopf-Berger sphere, but could be a round sphere. So here you also have round spheres.
Sorry, is there some restriction on the values of tau?
On the values of tau, no, because we are speaking about well position. So this theorem is not a general theorem. Then we will treat them. So there is more rich geometry for the not well position. So here we are in some way to the standard ones.
Okay.
We are concerned, and here you have that. So. So it's the same in normal coordinates, the same as you do in the sphere. So you have a total geodesic is the intersection of a sphere with a plane or with a subspace. But here in normal coordinates is the same. But of course you have not any plane or not any subspaces correspond to a totally geodesic. You have less of such things. Of course, this is not valid for dimension 1. O sea, in dimension 1, usually, but that you get. So these are the standard ones. So up to now, we are in the standard cases, and we have to fight a little and to do some calculation for obtain the standard ones. Well, see, here is what I said before. Totally geodesic well-positioned submanifold of Hopf-Berger sphere is either what I said before, because it's a geodesic sphere of a totally geodesic submanifold. A geodesic sphere is either a Hopf-Berger sphere if the totally geodesic submanifold has not constant curvature, and in the other case is a round sphere. So now we are several useful facts that so in general we want to draw the attention to general fact that could be more than the results we are discussing. General facts that could be useful for in another context. So first of all, we study the isotropy representation of the tangent space of the Hopf-Berger sphere. The isotropy representation. And this representation, this was known, this representation, not the action of H in M. This action is not polar, but the isotropy action, a linear action, this is polar, of codimension 2. It is very not difficult to see that the codimension is 2. It's not difficult to see the codimension is 2, and polar representation with codimension 2, so the principal orbits are isoparametric, but in codimension 2 it has to be a product of sphere. This is more or less, digamos, immediately once one sees, then one notices that the isotropy representation has codimension 2, the action. And then this is, so, and you don't get the full group that acts on this product of sphere. You get a smaller group, but there are smaller groups that act in product of spheres. I think there is an example of Dadok of some S7 acting transitively in product of spheres. But it's the other case. If you put if your Hopf-Berger sphere is the octonionic one, you have X15, and then the isotropy representation, the isotropy is spin 7, and spin 7 has represents on the tangent space, has two modules, the representation, one 8-dimensional and one 7-dimensional. In one modulus represents as in the standard representation of the orthogonal group, you pass, and the other is the standard spin representation. But what is nice is that you put so the orbits are still product of spheres, because in general, if you have a representation that decomposes a principal orbit, is not a product. But this is a known example of Dadok, that the polar representation, if you don't enlarge the group, could be so it's a group that is simple. So the orbits are product of spheres. So this is very, very important. And moreover, the principal isotropy, the isotropy of so you choose a vector, which is the principal vector, so that means that the horizontal and the vertical parts are not zero, no of them, and then you regard this isotropy action we are doing so in a linear space and the Euclidean space. Then we regard that the principal isotropy, the isotropy of the orbit of this product of sphere, and the isotropy representation of this has only one fixed vector. But why is important this? Because a principal isotropy fixes the normal vectors, because it's a principal orbit, and one more in the tangent. You have to do a calculation of that, and then you get a 3-dimensional totally geodesic submanifold, because the fixed set of isometries you are now regarding the ambient space gives rise to a 3-dimensional totally geodesic submanifold of the Hopf-Berger sphere. And this implies part 2. So any geodesic, so the direction of geodesic with the isotropy I put as a normal space of a principal orbit, and then after that, this direction lives in the 3-dimensional totally geodesic submanifold of the well positioned, because you have a horizontal space, and then the totally geodesic submanifold is given the direction by the horizontal direction that here the principal isotropy lives invariant, and then the normal direction to any sphere. So one implies 2. This is very important. Any geodesic is contained in a totally geodesic Berger sphere of dimension 3. Geodesic only. Okay. Third observation. A totally geodesic local submanifold. This is a very general fact, so it's difficult to find the proof of that in the literature. But a local submanifold extends to an immersed complete totally geodesic in homogeneous Riemannian manifolds. So a local extends to a complete. So to complete, so one has to be careful. So the complete is unique in the sense, if you want to say when the complete is unique, you have to go back to a concept, I think in the 60s, Herman, Robert Herman, is compatible totally geodesic submanifold. Compatible totally geodesic submanifold, that the totally geodesic submanifold can intersect itself, but then you since they are immersed, you consider the universal coverage, but then you pass to a quotient that you quotient the points that the immersion is the same, so the image is the same, but not the image, but the differential of the differential of the immersion of the tangent space is the same. Then you can pass, for example, in a closed geodesic. In a closed geodesic, you can pass to a geodesic defined in a circle. You can, digamos. So in that case, the totally geodesic is unique in this way.
Carlos, there
Yes,
are some comments in the,
sí.
chat. Marcos Alexandrino asked something.
Sí.
Hi, Carlos.
I
Welcome.
cannot see the comment, but I can.
Yes, Carlos. Terrible sorry to interrupt. Just one remark, I guess. This is probably true when the manifold is analytic. You probably can extend the total geodesic submanifold.
Yes, of course, you are right. You are right. When it's analytic, yes, you are completely right.
Okay, no, but terrible sorry to disturb, and welcome. Terrible sorry.
Yes, but it's difficult. So in a paper, also in the book, we wrote with Jürgen, and so it's difficult to find if you know a good reference for this. So please.
I will. I think I do have. I will send you by email.
Okay. Thank you very much. Yeah. Okay. Because we didn't find it, but this is very well known. So also we reconstruct the proof in some way, but of course we cannot publish a proof of this in order to be sure that it's okay. Okay. Thank you, Marcos.
I think this is even in the book with Renato, because this happens when you have this transnormal system. You have to extend those things, and so you have to close to the manifold in the Grassmannian. Yes.
Of course. I did not say
I
that
think it's in
the
chapter
formula
5.
we also check with your book with Renato, the formulas of the
No, but this extension is probably in chapter 5. Essentially, you consider geodesic disks, and lift them to the Grassmannian manifolds, and then use property of analyticity to glow those guys. And then you have this kind of arguments to see they are locally finite and then return. But anyway, I think it's in chapter 5, the reference there.
Okay, thank you.
But again, terrible sorry. It was something that I remember, but I probably start to forget everything. So terrible sorry, Carlos, terrible sorry.
Thank you. So, this general observation, this well-known fact, but thank you to Marcos, he gave me a reference. A complete totally geodesic immersive submanifold of dimension 2 of a compact homogeneous space is either compact, or this is a general fact also that we prove. So if you have a totally geodesic submanifold of dimension at least 2, you have a compact homogeneous geo space. So what happens is that the totally geodesic is intrinsically homogeneous, but it's not extrinsically homogeneous. There are also examples, and this is the main problem. So now, if you have a totally geodesic submanifold of geo space, there are two possibilities. Either it is compact, so the universal cover, so because you are in the category of immersions, or it has a two-dimensional totally geodesic flat submanifolds. So either, for example, a geodesic, this is one-dimensional, but of course, in a geospace, a geodesic needs not to be closed. In general, it's not closed. So here, it's not compact. But in general, we have this result, that the totally geodesic is either compact or it has a totally geodesic smaller submanifold of dimension 2 and flat. And then a calculation in positive curvature is clear. No Hopf-Berger sphere admits a flat totally geodesic submanifold of dimension greater than 1. And the proof is also simple because since the killings are bounded, then we can say that this tangent of this totally geodesic submanifold you can put as is part of a section of the polar action, the tangent space, and then the section of the polar action has dimension 2, and then you get this is inside a three-dimensional Berger sphere, because in 3 dimension it's a Berger sphere usually, but in 3-dimensional Berger spheres homogeneous has not submanifolds of totally geodesic hypersurfaces. So this would be the general proof, but that they are not totally geodesic. Okay. So this was very important because in a Hopf-Berger sphere, a totally geodesic submanifold is compact, but perhaps not one immersive. Perhaps so there could be self-intersections. So now we will speak about the slope of a tangent vector. The slope is just the quotient over the length of the vertical part over the horizontal part. This is the slope. And then since the isotropy acts, we do it for B with both components, component horizon in general. So a principal vector. So the horizontal and the vertical components are non-zero. And then the isotropy, since this is a product of spheres, acts transitively on the set of unit vectors with the same slope. This is very important. The same slope, and then the isotropy acts transitively. And also the slope of the tangent vector to a geodesic is well defined because the geodesics are one parameter group. And so the slope at any point does not change at any parameter. does not change. So we can speak about the slope of a geodesic. And so two vectors with the same slope, then the isotropy acts transitively. So also the set of slopes of closest geodesics in so this calculation you can go to the group using this match is played in the 3-Berger sphere because any geodesic is contained in a 3-Berger sphere. 3-dimensional Berger sphere, so you can do that and you can use the group and then you can prove that the set of since this space is naturally reductive, the set of slopes is countable and dense, but this is now it plays no matter, but so countable and dense. Okay, we are so we will regard the Hopf-Berger sphere as so.
Carlos, let
yes.
me tell you that we are almost on time. Maybe.
Yes. I have. We began 6 minutes, so we have. I think we have 3 minutes at least. No.
Okay. Perfect. Thank you.
Yeah. I take into account this. Okay. Of course, the geodesic sphere so less than the injectivity radio. So we are for non-well positioned total geodesic manifold. We will disregard, of course, the complex case, and then we will need the shape operator of the sphere. We put a t, depends on the radius, and then explicit calculation gives that. But what is very important now is that the shape operator is negative definite. We choose the outer unit normal. Is negative definite. Or the shape operator is negative definite for up to parameter. So it's negative in the non-compact case is always, but there is negative definite up to p/4. Because here the geodesic closes at time p, because not at time 2p, because of we put 4 as the maximal curvature. And then the shape operator is negative, and then if you prove you follow the proof of the system of convex neighborhoods. So the geodesic, if you go to the proof, the geodesic sphere is convex up to the sphere. The geodesic ball is convex up to parameter 1/2 of tau. So there is of tau. I mean of tau. Of course, I am translating to tau up to some t. The geodesic ball is convex, and then this implies that when the geodesic ball is convex, there will be the only one totally geodesic manifold are the standard ones. But we have to prove a different argument. But this is the reason. When up to so the geodesic close in at p then the geodesic is not more minimizing at p/2, and beginning at p/4, the geodesic spheres are not with parameter t of this radio. The geodesic spheres are not anymore convex. And now, so if the geodesic is not closed, so if our total geodesic, the submanifold does not contain the 3-Berger sphere that contains some geodesic, then the closure of the geodesic, but it's nice because it's given by the orbit of an abelian group, the closure of the group that gives the geodesic. This would give some intersection of dimension 2 with the 3-dimensional Berger sphere, and then is a contradiction And then, so what is very important for all is that all geodesics are closed. All geodesics are closed, and moreover, is a 2-point so projecting killing fields. We get so this is very important. That a no well-positioned symmetric space have all geodesics that are closed. Moreover, it is a rank 1 intrinsically a rank 1 symmetric space. And this, after that, we choose a totally geodesic manifold dimension 2 of constant curvature, and we do some calculation there. And what is important, so this is, so any two of them have the same slope. This is important because the slopes are discrete. And what is important, and the tangent the space to a not well-positional totally geodesic submanifold of Hopf-Berger sphere, the tangent space is light-like or isotropic with respect to the metric given by the second fundamental form. This was crucial because the non-well-positional now will be totally geodesic in the ambient space. This is the key fact. So it's either well-positional or it is totally geodesic in the ambient space, so in the symmetric space. So this is so here is what I said, not well-positioned, is isotropic with respect to the metric given by the second fundamental form, so the metric, the pseudo-Riemannian metric is isotropic, and this being isotropic means that the geodesics are the same as the geodesics of the ambient space, because alpha xx is 0. And then here we finish now. We put the classification explicit of this, and then there are some spheres, but some are not extrinsically homogeneous, and then we analyze the congruous class of the totally geodesic. We classify completely, but the key fact is so either it is well positioned or it is isotropic with respect to the second fundamental form. So you have to pass P over 4, and then so a totally geodesic manifold not well positioned is totally geodesic in the ambient space, so it is embedded. So we finished. Excuse me if I've used 2 minutes more. So thank you very much.
Okay. Thank you very much, Carlos.
In the link, thank you. So I put. So there is a in the drive. It is a talk, and also the talk in without pauses, so as a file only. So there.
Okay. It's there in the chat. Well, thank you very much.
Yes.
Yes. And are there some more questions or comments for Carlos?
Yes.
Yes, Marcos?
Oh, sorry. Carlos, I just put in the chat a reference for the scenes of extension. It is in the appendix of this paper.
Let me. Integrable Riemannian submersion with singularities. There.
Yes.
Okay.
Yes.
Thank you.
And that is appendix A, and this is the proposition.
In the appendix, it is proved it is proved.
Every small disk, every small totally geodesic disk in an analytic manifold can be extended to a immersed totally geodesic submanifold.
Okay. Thank you very much.
Please.
So in the appendix is there. So we will. So we have a preprint in the archive.
No, it's but it doesn't discuss how to have this homogeneous structure in the sections and things like that. It's just a curiosum. It's just I don't know if it helps somehow. I'm just giving something that I remember. Certainly, what you have talked is there is much more information than what is in this appendix. This appendix is just a remark that the extension is not a big problem, but to have the other structures that you told, of course, then
Okay. Okay, thank you.
it's just to say about extension, not about everything.
About extension.
Yes.
Okay. So we will see the paper. So I will. You send me by mail or to the?
No, it's in
I
the
can
chat.
send you. It's in the chat.
In the chat. No, because I put in the mail because then otherwise I lose.
Okay.
in the mail.
Yes. I needed your email probably.
Okay. So it's a paper of yours and.
Yeah. No, that's one of my first papers. At that time, I had to work alone.
Integral Riemannian submersion with singularities. So geometria dedicata, O4. Okay. Thank you very much. So we will in some days we will put a new, because we will.
No, don't worry. It was just
but
more
not
a remark.
also because we have to put a new one, and so we can add to the bibliography. So we have the introduction was very long. That we put in the archive, and then we will simplify something. But the paper is the same.
Are there any other questions or remarks for Carlos? So about these not well-positioned submanifolds,
Yes.
diffeomorphism types are always spheres or projective spaces?
They are spheres or projective spaces.
Yeah. Okay.
Yeah, and they are in the table in the last part of the top. So they are the classification model of the isometry group.
Okay. And that includes the exceptional case that you mentioned in the first part.
No, exceptional I put some for the talk because in some way, because the others you can construct in some geometric way. You get the fiber and then. Or you bring back the fiber by parallel transporting the ambient space, but the curve that is perpendicular, a horizontal curve, but is perpendicular to this, and then the parallel transport in the ambient space turns out to be in the same as in the geodesic sphere, and then we wait some time up to this to be isotropic. So there is some trick, the general trick that we can achieve of that. But the others, no, you have to do calculations, so to use conditions and then brute force. So.
Okay, thanks. Okay, are there any other questions for Carlos? Well, if not, let's. Do you have one? Okay.
No. It's just we're gonna have to go.
Okay, so well, let's thank the speaker for his very nice talk, and thank you all for coming today.